So we're going to talk through, this is in the textbook, but obviously we just have it right here on page 152, number 6, because now we're talking about on an incline, dealing with the x and y components when we're having to tilt our axis. So this is going to get a little bit more confusing, but the concept is going to be the same like we were talking about today. This brick is at rest. Now, because it's at rest on an incline, what that means is there's friction, right? The only way for something to be at rest on an incline is if there's enough friction to prevent it from sliding. So even though it doesn't say there's friction, if there's an incline and we say something is at rest, there is friction. So again, what we're focusing on here is going to be the x and y components, making sure they add to zero, doing stuff like that. But we're tilting our axis, so it is going to be a little confusing. So let's go ahead and follow along with this. So to start with, we need to identify each of the forces exerted on the brick. There are 3 forces exerted on this brick. Go ahead and identify them. Just write them out. You don't need to label them yet on the picture. Okay, the forces are the force of gravity. Because we're on a surface, we have the normal force. And because, like I said, the brick is at rest on an incline, means there is friction. So these are the 3 forces at work here on this brick. So now we're going to go ahead and draw a picture of our system. We're also going to draw the x and y coordinate system we're going to use. So here is my incline and my brick. I have gravity pointing straight down. Now what I'm going to do first, actually I lied, I'm going to backtrack. I'm going to go ahead and draw my x and y axis first, and then I will draw my forces. So here is my x and y axis. I'm going to go ahead and draw this in a different color so it's easier to see. The origin is the center of the brick, which is why I'm going to draw my x-axis a little bit above my incline. There is my x and y axis. So with that in mind, now I'm going to go ahead and just erase my incline. Because again, we always draw coming from the center of the object, the center of its mass. Okay, so let's go ahead and let's draw our force vectors then. I want you to take a moment and draw them. Gravity points straight down. Even though we're on a tilted axis, gravity points straight down. Normal force points perpendicular to the surface. Friction points opposite to the direction it would be traveling if it were sliding down, even though it's not. Go ahead and try and draw these forces. Okay, here is the force of gravity. It points straight down. Now, we are not going to label gravity as a negative. We're going to talk later about why, but we talked about it in class anyways. Gravity is not lying exactly on the axis, so it cannot be labeled a positive or negative in this case. Its components can be labeled positive or negative, and we will do that later. Right now, gravity is just plain old gravity. The normal force, though, is going to be considered positive because the normal force lies perpendicular to the surface. It's lying exactly on the y-axis, and that's going to be a positive. And the force of friction is going to go this direction. Because it's pointed that way, if you tilt your head, that's positive x territory. So that's actually a positive friction. Again, if the block were sliding down, it would go this way. So friction fights against the motion of travel. There is enough friction here that we are not moving, right? So here's what we need. Since this brick is not moving, what that means is it's in equilibrium, right? If we are in equilibrium, it's going to be at rest. Or possibly, again, we talk about later, constant motion. Don't worry about that right now. So what we need to show is why it's in equilibrium, or what would be true, because we don't really know much about this brick. For right now, we're ignoring the fact that it's 2.5 kilograms. We could do a bit more with that later. We're going to do that later. Right now, we're going to kind of ignore that. What we do have though is remember that when we label the angle, I am going to go ahead and add that angle on there. The angle is always in between gravity and the y-axis. So I'm going to say that again, and then I want you to try labeling it. The angle goes in between where gravity is at and the y-axis. Label the 15 degrees on here. Okay, so 15 degrees is going to go right here. When we go an incline, that's where the angle is also coming from. Yes, we could say the angle comes from over here, but we can also move it to over here. That's 15 degrees. Okay, so here's our situation. Let's go ahead and let's look down. What we're going to show is, since this is an equilibrium, we're going to show that the x components are going to add to 0 and the y components are going to add to 0. So, or again, that they would need to. So what we need to do, again, let's look at all the components that we do have. Here are my x components. This is always a good idea to label them before we start. Now there's one direct x component right here, right? The force of friction is an x component because it is only an x component. It's only in the x direction. But we also have another x component, even though it's not labeled on this graph. It is the x component of gravity. This right here is going to be the x component of gravity. So here's my two x components, the force of friction and the force of gravity in the x direction. What I'm going to show is that those are equal but opposite. They would add to 0 because this brick is not moving, right? Gravity pulling it down this way in the x direction, it's not going to be strong enough to fight against the friction, and they need to be equal. Let's talk about the y components then. So my y components, we can see that again, the normal force is strictly a y component. And we also have a y component for gravity. So I'm going to show, once again, this is going to be the goal of this question, that my x components will be opposite and equal, and my y components will be opposite but equal. Again, that means if you were to add them together, they would be 0. So let's go ahead and let's look at the x component for gravity. Now, we have to be very careful here, guys, how you draw this. Here is gravity. Ooh. I'm going to tilt my picture a little bit here, guys. Do I want to do that, or is that more confusing? I'm going to try to keep it consistent. Here's gravity. Nah, I'm going to tilt this back. So usually when I look at gravity, guys, I draw a separate triangle, making gravity the hypotenuse. Because if you can see right here, this vector is the hypotenuse of both of those triangles we're looking at. So usually if I'm trying to focus on gravity, I redraw it separately with gravity as the hypotenuse. And here's my right angle. So what I'm doing right here is I am taking this triangle, and I'm going to just go ahead and tilt it flat. So the 15 degrees is up here. Let's think about this real quick. If I'm tilting that, this component down here is going to be the same as this component up here. So is this going to be my x or my y component? That's the x component. Ooh, do I want to do it this way? We're going to do it this way. I'm going to show you how we do it this way. And because the x component, which is again right here and right here, is going in this direction to the left, is that going to be a positive or a negative x? That's a negative x. Okay. Now, again, this triangle is just being tilted, and this is what we're looking at right here. Then this component is my y component of gravity. Yes, if this is my x component, this is my y component of gravity. And once again, because it is here, is that going to be a positive or a negative y? Negative. So here's what I'm looking at. Now, here's where you can't go too fast. when we do the trig, we are going to do the trig to break it down to figure out these angles. Notice that now x is your opposite and y is your adjacent. What that means then is, because of where the angle is at, sine is going to be used for x and cosine is now going to be used for y. Sometimes if we change where the angle is coming from, those can flip. This is what I was saying with be careful. Y is not always sine depending on which angle we use. If you wanted to find this angle right here, y would be sine and then x would be cosine like normal. But if I just want to pull this triangle down, since x is the opposite, now x is going to be sine. Now, I'm going to go ahead and show you this. We do not know the magnitude of the force of gravity. Yeah, we could, but we're going to kind of ignore that for right now. But we know this is the magnitude of the vector. So remember the trick. It's the magnitude of the total vector times the trig function. And again, because x is the opposite, x is now going to use sine of 15 degrees. And one more thing I need to add on, it's a negative because it's a negative x. Go ahead and write out for this next one then what the y component would be. Y is now the adjacent. Now we're going to use cosine, but it's going to look very similar. Go ahead and try the y component. Okay, the y component is going to be negative, once again, we said it's a negative y, times the magnitude of the hypotenuse. Now we're using cosine. And we're going to leave it like that. So here's my x component, here's my y component. So let's go ahead and go on to the next part. It's express the net force exerted in the y direction in terms of the y component. So let's look back up. We said our y components were the normal force and the force of gravity in the y direction. So here's the force of gravity in the x direction. Here's the force of gravity in the y direction. A net force means to add your forces together. So my y forces were the force normal plus the force of gravity in the y direction, right? So here's what I've got. Force normal is just force normal, but my y component is right here. That's my y component, minus the force of gravity times cosine 15. Now, because my brick is not moving, what should these equal when I add them together? This brick is in equilibrium. What should those equal? 0. And in fact, even if the brick was sliding down the incline, because we're talking about the y direction, even if the brick is sliding, these forces would still add to 0 because that's what keeps the brick on the incline. Yeah, it's fine. It's just sitting there on the incline even if it's sliding. So they should equal 0. So go ahead now and let's try to express the net force adding our x components together. Look back to what you have. We wrote up top what your x components are. Add them together and say what they should equal since this brick is not moving. Okay, we said our x components were the force of friction and the force of gravity in the x direction. Force of friction plus, again, the force of gravity in the x direction is what we're doing. Net force, add the forces together. Now we have the force of friction, and now we know the x component, negative Fg sine 15. Now, what should these equal again? Because this brick is not moving, 0. The force of gravity in the x direction is not great enough to fight against friction. As we continue to increase the angle, if this were a bigger angle, eventually that's why it would start to slide. This would eventually get bigger than the force of friction, and the brick would start to slide as we increase that angle. So because this brick is in equilibrium and it's lying on a surface, the y directions add to 0 because it's on a surface. If you're on a surface, the y directions will always add to 0. But the x directions also add to 0 because it's not moving. They're equal but opposite in direction forces. So tomorrow we're going to do a bit more practice with this using actual numbers.